In the previous chapter, we saw how space is allocated in the memory for a variable. Now it's time to look at how long will the piece of memory stay assigned to a particular variable. This is determined by the storage class of the variable. Storage class of the variable defines the life of a variable, which is nothing but the duration for which the memory will stay assigned to that variable. Basically, there are two types of storage classes. They are automatic and static. Automatic storage means that the memory is allocated for the variable when the control enters the block where the variable is defined. And the same memory will be discarded the moment we exit the block. By discard, it just means that the memory doesn't belong to that variable anymore. There is a misconception that, when we exit a block, all the automatic variables are destroyed, and their memory is not accessible. The program can crash if it tries to access that memory. The memory is not accessible is not completely true. It is just that the memory that was allocated for the variable will no longer belong to it, and can be reused by others. Hence, after the block, even though the memory is accessible, it is not guaranteed to contain the value of the variable to which it was allocated. That's what is really meant by saying the automatic variables are destroyed when we exit the block. This will make more sense when we discuss about local variables and stack frames in later chapters. The variables with automatic storage can be allocated memory in the stack or the hardware registers. They are sometimes again called as auto and register storage class respectively. Static storage means that the memory allocated for a variable will stay assigned to it until the end of the program, or till the module in which the variable is defined is unloaded. That memory will never be reused by any other variables. It's like the memory is permanently assigned to that variable. The static storage class can again be classified as external or static based on its scope. The memory for static storage class is allocated in the data segment of the program. If you don't know what is data segment, don't worry. We would discuss it later on in the course. For now, just remember that memory for static storage is allocated in the data segment. Scope of a variable is the area in the program where the variable is accessible. It is usually the block in which the variable was defined. Whereas, the life of a variable is the duration within the program where the variable can retain its value. That is, until the memory allocated for the variable stays assigned to it. Life of a variable is defined by its storage class. The variables with automatic storage class can retain value only within the block where it was defined. The moment block is exited, the memory assigned to the variable is discarded, and life of the variable ends. But with static storage, the memory belongs to the variable until the program ends. Hence, the variable is alive throughout the program execution time. Let's take a small program to look at the scope and life of various variables used in it. Let's begin with main function. It defines two variables with automatic storage class. The variable I is given memory in the stack, whereas the variable k is allocated in register of the processor. Since the variable have automatic storage, the life of the variable is only within the block where it is defined. Same is true for its scope. Hence, for variables I and k, the life and scope is the main function. These variables will not be accessible outside main function, and the moment control exits the main function, the memory assigned to these variables are discarded. Now let's look at the function foo. It defines two variables, a and b. The variable a is defined with the keyword static, which defines a with a static storage class. Since the memory for static storage class is never discarded, the life of variable a is that of the program. But since variable a is defined inside the foo function, its scope is only within the foo block. The other variable b has automatic storage class, hence its scope and life is the foo block, where it is defined. Now let's look at the variable g, which is defined outside all the functions. This has a static storage class by default. And since it is not defined within a block, its life and scope is throughout the program. This is also called as global variables. I hope this program clarifies where and how long will a variable retain its value. Now let's look at the sections of an executable file, and see how they are related to the storage classes that we discussed in the previous slides. Any executable has three main sections. They are text, data and BSS sections. As the name suggests, the text section contains the code for the program. It has the assembly instructions for all the functions that are defined in the program. The next section is data section. It contains all the hard-coded values used in the program. And the last one is BSS section, or block started by symbols section. It contains a number, which is the sum of sizes of all the uninitialized variables that have static storage class. We would look at each of these sections in detail in next few slides. Let's look at a small program and map the program to the sections in the executable, which will be created when the program is compiled. The program defines two functions, main and foo. These functions uses some local and static variables. The program uses some global variables too. When this program is compiled, the text section will be made up of the instructions for main and foo function. When the program is executed, the instructions in this section are scheduled by the operating system to run on the processor. Now let's see what is the data section for this program. As we said in the previous slide, all the hard-coded values used in the program are saved in this section. But please keep in mind that only the values which are related to variables with static storage will be saved in the data section. The values are saved here because the instructions might need to access it as per the code logic written in the program. For example, the value of variable h is initialized to 10 in the program. This value 10 is needed during the execution phase. Hence this value 10 is saved in the data section. And this piece of memory is the space given to the variable h. So whenever the instructions try to access the variable h, it will access this part of data section, where 10 was saved. That's why we said earlier that the memory given to the static storage class variable is permanently assigned to it. Same way other initialized variables too are saved in the data section. Like, value of variable j which is 21, variable b which is 63, and the string used in the printf function. But please note that the value of variable a, which is 42, will not be saved in the data section since a doesn't have static storage. Instead, the value of 42 is hard-coded in the instruction of foo function, which initializes the variable a. This instruction will initialize the memory allocated to variable a whenever the foo function is entered. That's the reason why variable a will always have the value 42 when we enter the foo function. But the variable b is not initialized using instructions. Instead, when foo function is entered, it will directly start using the value saved in the data section for variable b. So in the first invocation of the foo function, the value of variable b will be 63. If the value is changed, next time when foo function is entered, it will see the new value in data section. I hope now you know why static variables are able to retain their values across function calls. And now the last section, BSS. This section contains a number, which is the sum of all the sizes of the uninitialized variables with static storage class. As we know, the static storage class variables have to be given memory in the data section. In data section, we saw how memory is given to initialized variables. But we should give memory to uninitialized static storage class variables too. That's where BSS section is used. This number saved in the BSS section tells the operating system how much more memory is needed to accommodate uninitialized variables in the data segment. So, all the uninitialized variables with static storage class are given memory in this extra area. For the code given here, the BSS section will contain the sum of the sizes of the variables g and I, which would be 8 bytes in a 32-bit program. You might be wondering what happens to the local variables. It was not allocated in any of the sections. That's because the memory for local variables are created in the stack segment as and when required by the code at the runtime. After the block is exited, which had the local variable, the memory on the stack that was set aside for it is discarded. We would discuss how this is done later in the course. In the previous slides we saw how sections in an executable are created and what it contains. Now let's see how are these sections used by the operating system to execute a binary. On most of the operating systems, to execute a binary, it has to create a process and allocate at least 3 main segments. They are text, data and stack segment. The text segment will be filled with the instructions that have to be executed, and data segment will contain all the data that is needed by the process at runtime. And the last one is stack segment, which is used to create function stack frames and local variable. To create the text segment for the process, the operating system just reads the text section from the executable and copies to the text segment in the process image. To begin the execution of the process, the program control is passed to the entry function in the text segment. But before the program execution can begin, it has to first create the data and the stack segment. The data segment is created for allocation of variables of static storage class and other hard-coded values used in the program. To create the data segment for the process, the operating system or the process loader reads the data section from the executable and copies it to the data segment area in the process address space. Then the process loader reads the BSS section and extends the data segment area by the value given in the BSS section, and initializes the extended area with 0. This extended space is used by uninitialized static storage class variables. This way, both the initialized and uninitialized variables with static storage class are allocated memory in the data segment. Since the extended memory is initialized to 0, the initial values of any uninitialized static or global variable is 0 in a C program. The last one is stack segment. This is used for memory allocations at runtime. We would discuss this later on in the course.